Since in the last lecture we are studying the differences. Okay, so we have a problem that you have solved. I think for the shift operator you have solved, right? Right, you
Yes.
have solved for the shift operator, no?
Yes, sir.
Yes. Okay. So I hope you are able to see this.
Yes, sir.
Okay.
Yes,
So
sir.
let us go for that problem. Okay. We have seen in the last lecture. Okay. So the example was find delta f of x and del f of x for f of x is equal to x square plus x. Yeah, where h is going to be 1. Okay, so with h is equal to 1. So let's go for the solution. So what we know, let f of x is equal to, so we have x square plus x. Okay. Hence, what we do is we consider delta f of x. So what we'll have, we have f of x plus 1 minus f of x. So is that okay?
Yes, sir.
Okay. So what will be having f of x plus 1? So it will be x plus 1 bracket square plus x plus 1. Okay. So we have this x will get replaced by x plus 1. Okay. And minus. So f of x. So it is going to be x square plus x. Let us simplify this. So we'll be having x square plus 2x plus 1 plus x plus 1 minus we have x square plus x. So if we simplify x square plus 3x and we'll be having plus 2 and you'll be having minus x square plus x. So here we get x square plus 3x plus 2 minus x square minus x. Okay. Now what we can have, this is equal to, so x square we have here we have x square, so that will get cancelled. Then we have 3x minus x, so it will be 2x plus 2, and that is going to be delta f of x. So this is what we have. Okay. Now what we want to find out, we want to find out del f of x. Okay. So now we consider. So what we want, del of f of x, and that's what we'll be having, f of x minus f of x minus 1. Is that okay? Are you getting this formula?
Yes, sir.
Okay. So what we have here, this is x square plus x minus, this is x minus 1 square and plus x minus 1. Okay, as our function is x square plus x, so x will be replaced by x minus 1. Let us simplify. So we have x square plus x minus, this will be x square minus 2x plus 1 plus x minus 1. Now what we have here, x square plus x minus x square minus x, and this plus 1 minus 1 will be 0. Okay, so that's what we can have. Now simplify x square plus x minus x square and minus minus plus x. Is that okay?
Yes, sir.
This will be minus and this will be minus minus plus. Okay, and hence what we get here, L f of x is equal to. So this x square will get cancelled and you'll be having 2x. So that's what we have here. So we got the del f of x is equal to 2x, and we got delta f of x is equal to x plus 2. So all of you got the same answer?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, that's good. So all of you got the same answer. Very good. Okay, now in the last lecture, we have discussed about the error propagation. Okay, so how the error propagates. Okay, so if I know that there is certain term which is in error, and if I know the degree of the polynomial which approximates that values, or where the values are followed by that particular polynomial, then we have to understand that whatever the degree we have, okay, so suppose we have nth degree polynomial, okay, then the nth difference will be constant. Okay, this is very important thing that you need to understand. If we have nth degree polynomial, then its nth difference, okay, whether it is forward difference, whether it is backward difference, will be constant. Okay, so that means all that n differences will be same. Okay, it is going to be constant. That means all the differences will be same. Okay, so using this, we try to correct the values. Okay, so what we have to note that if polynomial is of degree n, then nth difference is okay. So we have this nth degree polynomial and its nth degree difference is going to be constant. Okay, now we have to use this, and then we have to correct the values. Okay, so let us try to understand this using one example. Okay, so let's go for the example.
Sir, can you show the last slide once again, please?
Yes, yes, surely I'll. Okay, are you able to see this?
Yes, sir.
If the polynomial is of degree n, then nth difference is constant. Okay, so all the nth differences will be same. What is meant by constant? They will be same. Okay, so let's try to go for an example. Okay, so are you able to see this? Are you able to see this?
Yes, sir.
Yes. Okay, so see, we have the example. So this table gives the values of a polynomial of degree 5. Okay, so it gives the values of a polynomial of degree 5. Okay, so from this, what you can say? These are the values for the polynomial of degree 5. So what do you get? Its fifth difference will be constant,
Yes, sir.
Yes, sir.
isn't it? Its fifth difference is going to be constant. Okay, so now it is given that f of 4 is in error. Okay, So what we have, f of 4 is in error. So that means this value is in error. So this is the value which is in error. And now the question is, we have to correct the value of f of. Okay, so we know two things. One we know is this all values are followed by a fifth degree polynomial, and then this value f of 4 is in error. And if the fifth degree polynomial is there, that means fifth difference is constant. Okay, so what we have to do is we have to find the difference table. Okay, so let us try to find the difference table. Okay, so we go with the solution. Okay, let y is equal to f of x be the polynomial of degree. Hence,
So,
the difference. Okay, so what will have? Hence,
hello, sir.
yes,
So, what do we have to find? Correct value of f of 4.
yes, we have to find out this value. We know it is in error, so we have to correct this value. Okay, so we have to find out the correct value of f of 4. Okay, so as we know, the error will propagate. No, we have seen in the last lecture that how the error propagates in the coming differences. Okay, and it makes its multiple copies. Okay, so what we have to do is first we have to find out the table and then correct this value. Okay, and once we correct this value, then your predictions or your interpolation will be correct. Okay, otherwise it will be with the error. Got it? That's why we have to correct this. Okay.
So,
Yes. Okay. So hence, fifth differences will be constant. Okay. So that's what we have. So we have the following table. Okay. So now I want you to make the table. Okay. So let us see. So we have x, we have y, then we have delta y, delta square y, delta cube y, delta raised to 4 y, and what we know, delta raised to 5 is going to be constant. Okay, so this term is going to be constant. Okay, so we have to find up to this because it is given that the polynomial is of degree 5. So we have 1 to 7. Okay, so this is going to be 1. We know the difference table, the construction of difference table. So one line we have to leave. It is going to be 3. It's going to be 4. Five. Please construct the table. Okay. we have 6 and we have 7. So this is how your table should be. Now see what we have the first value. We have the first value 0.975. This is minus 0.6038083. 6083. We have minus 3.5250. And this value is in error. Okay, so what we say, if this value is in error, then we write this as
Plus epsilon.
plus epsilon. Okay, so it will be minus 5.5250 plus epsilon. Okay, so this value is in error and we have to correct this value. So we write it minus 5.5250 plus epsilon. Then we have the next value is minus 6.3583. So this is minus 6.3583. 3583. Then we have 4.2250. So we have 4.2250. And we have is 36.4750. 36.4750. So we have 36.4750. Yes. So we have 36.4750. Okay. So these are the values of y given and x given. Now we have to find out all the differences. Okay. So please complete this table. Okay. So I want you to complete this table.
Sir, can you scroll down a little bit?
Yes.
Sir, no, I want to see the question.
Okay. This is the question.
Thank you, sir.
Yeah. Calculate this table. So I hope all of you are ready with the table now. So your table should look like this. Okay. So are you getting your table like this?
Yes.
These are the calculations that you are supposed to get. Maybe approximated again. Okay.
Yes.
Calculations will be nearby this. Okay. Now we know that this is the 5th degree polynomial. Okay. So this is a polynomial of degree 5, and hence we know the 5th difference is going to be constant. Okay. So what it means right here, since y is equal to f of x is of degree 5, hence the 5th difference of y is constant. Okay, so that is what you can say is this 12 plus 10 epsilon, okay, is same as minus 10 epsilon. Okay, so what we get here, so we can have this epsilon on the other hand side, okay, and this 12 on the other hand side. So what we get here, we get is going to be 20 epsilon is equal to minus 22, or we can have this is going to be epsilon is equal to minus 22 by 20. And now what you'll be having, this is minus 1.1. Is that okay? Are you getting this? So epsilon we get minus 1. So what was the error there? There is error of this term, and hence we want to find out the correct value of 4 or f at 4. So the correct value of f of 4 is, so what you'll be having, f of 4 equal to minus 5 point. So what is the value given? This is 5.52
525.
50. Okay, minus 5.5250, and the error is minus 1.1. So this will become minus 6.6250. So this will be yes. So we got the value f of 4. The correct value is minus 6.625. Okay, so your value, whatever you approximated, should be nearby this.
So
Okay.
please scroll up a little the table.
Yes. Okay. So that's what we have. Okay. So if you are having difference in last digits, it's okay. But approximate value should be nearby this. Okay, all of you got these values?
Yes, sir. Got.
Yes, sir.
Okay. So it's good. We are able to correct this value. Okay. Now we'll try one more example for the error propagation. Okay. So let's go for another example. I hope you are able to see this.
Yes, sir.
Yeah. So we have another polynomial, okay, of degree 5 again. Okay. And it follows this data. Here it is given that f of 3 is in error. Okay, so this term is in error. So what we have to do is we have to correct this value. Okay, so let's go with the solution. So what we'll be having, let y is equal to f of x be polynomial of degree 5. Okay, so what do we have? Hence, fifth difference of y is constant. Okay, so what we do is consider the following difference table. Okay, so let us construct the difference table. Okay, so how we are able to construct this difference table? Again, same as we construct. So we have x, we have y, we have delta y, delta square y, delta cube y, delta raised to 4 y, delta raised to 5 y. Okay, so as we know, the difference is going to be 0 if the difference is a constant. Okay, so think of this differences. Okay, and we know now f of 3 is in error. We have 0, 0, 1, 2. We have here it's going to be 3. Here we have 4. Now we can see we have 1, 2, 33. So this is 1, 2, 33. And this value f of 3 is in error. So 254 is in error. So that means it will be 254 plus epsilon. Okay. And we can have this 4, 5, and 6. Okay. So we have 4, 5, and 6. What are these values? 1054. 1054. We have 3126. 3126. And we have 7777. Now let us calculate the first difference. So it is going to be 1. Second difference is 31. This difference you have to calculate. So please calculate this table till the fifth difference. Okay, so calculate this table. These are all integers, so you can calculate easily. So please calculate this table. Okay, so I hope you are ready with the table. Okay, and you can verify your table with this. So I hope all of you have got your table like this. Okay, so here, as we know, this is the 5th degree polynomial. Okay, so what we have to do is its fifth difference is going to be constant. Okay, and hence we have okay. So what do we get here? 220. Yes.
Sir, in the first difference between 4 and 3, it should be 800, no?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, this has to be. Okay, so I hope you need to tell me what these two figures are. Please give me this difference. What this difference is?
Sir, minus 141 plus 10 epsilon.
Okay, so it is going to be
Sir, I am getting
minus
75 plus 10 epsilon.
41.
Sir, 75 plus 10
Sir,
epsilon.
75 plus 10 epsilon.
75 plus 10.
Okay, so we need to be careful.
75 plus 10 epsilon.
So it is going to be 75 plus
10 epsilon.
So plus 75.
plus 75. Okay. So it is going to be plus 75 plus 10 epsilon is equal to what this figure is?
310 minus 10 epsilon.
Minus 10 epsilon. Okay. So fine. What we get then here? So we'll be having this is 20 epsilon is equal to 75. I'll have on the other hand side. And what then I'll be having? Is it 235? What is the value you get here? Is it 235?
Yes, sir.
So we get here is going to be 235. And hence, what will be the epsilon? Epsilon will be 235 by 20. So what value you got here?
11.75.
11.75. So we got epsilon is equal to 11.75. And hence, the correct value of f of 3 is, so what we have, f of 3 is equal to 254 plus epsilon. So that is 254 plus 11.75. So we got f of 3 is equal to, so it will be 265.75. Is that okay?
Yes, sir.
So this is how we are able to find the error, and we are able to correct the value, provided that we know the degree of the polynomial. Okay, so if we know the degree of the polynomial, then we are able to find the constant difference. And once we know which difference is going to be constant, then by constructing the table, we are able to find what two terms are going to be same. And once we know these two terms are same or equal, so we can find the value of epsilon. Once we know the value of epsilon, we are able to correct the given value with the error. Okay, so that's what we have. Okay, so is there any doubt in these two examples?
No, sir.
Yes,
No,
all of
sir.
you got these two examples?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, that's good. Okay. In the last problem, we have corrected the table. So I hope you are getting this table, right? This is what the table you will have. Okay, so now we know how to correct the error, or how to find the error, and then how to correct the term. Okay, so we have corrected the term. We know how the error propagates and how we are able to catch it and then correct it, provided that we know the degree of the polynomial which approximate or which is followed by the given observations. Okay, so here we have got this value. Now we have to see some properties of these operators. Okay, so we have seen the forward difference operator, we have seen the backward difference operator, we have also seen the forward shift operator and backward shift operator. And we have also considered the central difference. Okay, so now we have to consider the average operator or average distance difference. Okay, so what we have here, okay, so for average, we use mu as a notation. Okay, so what we do for the average, if we want to find out average of two numbers, what we do, we just add these two numbers and then we divide it by 2. Again, so here, if we want to understand average operator, okay, so we use the letter mu. Okay, and what we have here, so we have mu of f of x. Okay, this is going to be the average of the next half and the previous half. So it is half of f of x plus h by 2 and plus f of x minus h by 2. Okay, so this is the next half and this is the previous half. We are finding the average of this two. Okay, or also if we consider mu of f of x plus h by 2, then it is going to be half of f of x plus h and plus this is f of x. So are you getting this? When we have to consider the average operator, we have to add h by 2 and then subtract h by 2 from the current position. So whatever we have this here. Okay, so here I have plus h by 2. So add h by 2, it will become h. And subtract h by 2, it will become f of x. Okay. So in central difference, we consider minus here. In average, we consider plus and then half of that. Okay, so that we are able to get the average of these two quantities. Okay, and that's why it is going to be the average operator. So then we know differential operator. So we have expressed the shift operator, forward shift operator and backward shift operator in terms of the difference operator. So what we have, d of f of x is nothing but a dash of x. Okay, so that is the difference operator we have considered. Okay, so once we know the difference operator and this average operator, so we can have the all operators, okay, in one table as, so here we know the forward difference, we know the backward difference and all other operators. Hence, consider the following. So here I'm giving you all operators one table. So you can see here we have the forward difference, here we have the backward difference, then we have the central difference, then we have the shift operator, then average operator and differential operator. Okay, so now we'll see some properties of the operators. Okay, so we go for properties of operators. Moreover, we need to understand that all the operators follow very similar properties. Okay.
So can you please scroll up a little?
Yes, just wait. Okay, so here we have defined the average operator and now the differential operator. And here in this table, I have taken all the operators together. Okay, so we have forward difference, backward difference, central difference, shift operator, average operator, and then differential operator with their notations. Okay, Now we need to understand the properties of the operator. So first we consider, as I said, all of this operator follow very same property or similar properties. So if we consider, let f of x be a constant. Okay, so constant function. This is going to be constant function. Now consider. So what we consider forward difference of this f of x. So what we can have, we have f of x plus h minus f of x, right? Since f of x is constant, so we have f of x plus h is equal to c, and f of x is also c, because f of x is going to be constant. So what we get here, delta f of x is equal to c minus c, and that is going to be 0. So what we got here, we got that delta f of x is equal to 0. So what we can say here, if we operate the forward difference on a constant function, then the difference is going to be 0. Similarly, this property is applicable for the backward difference. Okay, because the backward difference of constant function is also 0. Because you will be having the previous value is same as the current value. Here, the next value is same as the current value, and that's why this forward difference as well as the backward difference is going to be 0. Okay. Moreover, these differences are linear operator. Okay, these are also linear operator. So what we can have, suppose let f of x and g of x are functions of x, then what will be having delta f of x plus or minus g of x is nothing but delta f of x plus or minus delta g of x. So this property is called as linearity property. And moreover, let f of x be the function of x and c be the constant. Okay, then we have delta of c times f of x is equal to c times delta of. So if we have a scalar with the function, okay, this is a scalar and this is the function. So if we have the scalar with the function, then we can take this scalar out, and then we can see the difference of the function. Okay. So is there any doubt up to 8?
No, sir.
No, sir.
Sir, can you please show the screen?
Yes. Okay. So is there any doubt up to 8? All of you are able to get up to this?
Yes, sir.
Yes, sir.
Okay, good. Okay, so now we'll try to solve some problems based on the properties. Okay, so we know the basic some relation that we have already proved in the last lecture. Okay, so I'm going to use that, or that's why I have given you this table, so we can easily use the definition, and then we are able to find. Okay, so we'll go with the example. So that shift delta is same as delta shift. Okay, so we have to show that these two operators commute. Okay, so if I have to operate these two operators, okay, what will happen? Okay, either any operator I can operate first, and any operator I can operate later. So this is the mean by commute. Okay, so here we can go with the solution. So what we have to operate this operator on some function. So let us assume some function. So let f of x be the function of x. So consider, okay, shift and delta of f of x. Okay, so we have to think of the shift and delta operated on this f of x. So let us try to operate, okay, and then we'll see what happens. Okay, so here we'll operate delta first. So shift of delta f of x, and we know what is the value of this. So it is shift of f of x plus h minus f of x. Is that okay? Are you getting
Yes, sir.
this? Yes. Okay. And as we know, this is a linear operator. So we can say shift of f of x plus h minus shift of f of x. So we can write this will be f of x plus 2h minus this is f of x plus h. Is that okay? Are you getting this? So what do we know? What is the shift operator? Since the shift of f of x is equal to f of x plus h. So when we use a shift operator, this h is increased, x is increased by h. Okay, so here this x is increased by h. This x plus h will be increased by h again. So it is going to be 2h. Now, can I write this term as delta of f of x plus h? Can we write it like this? So this is f of x plus h plus h minus f of x plus h. So this is x plus h. So this is x plus h plus h. And so we can say, okay, that this is delta of this term. So we can say this is delta of shift of f of x. What is that? This is delta, and this is shift of f of x. So what we got here, we got shift delta of f of x is same as delta shift of f of x. Okay, and hence we can say that these two operators shift delta is same as delta shift. Delta is same as delta shift. So is there any doubt this example? Is there any doubt in this example?
No, sir.
All of you got this one?
Yes.
Yes. Okay. So now let us try to calculate something else. So let's go for another example. Calculate delta square upon E operated on x cube with step size. Okay, so here the step size is given to be h. Okay, now using this we have to calculate this operator operated on this term. Okay, so we go with the solution. We have let h be the step size and we have f of x is equal to x cube. So consider delta square upon E operated on f of x is equal to delta square upon E operated on x cube. So can we write it like this? Delta square e raised to minus 1 operated on x cube. Is that okay?
Yes, sir.
Okay. So what we have, since we know what is delta, delta is e minus 1. Is that okay?
Yes, sir.
Delta is e minus 1, no? So I'll write here, this is e minus 1 bracket square into e inverse and operated on x. Okay. So let us try to simplify this. So what we get here, this is e square minus 2e plus 1 and this is e raised to minus 1 operated on x. So what we get here, this is e square into e raised to minus 1 is going to be minus 2 and we'll be having plus e raised to minus 1 operated on x cube. Is that okay? We're getting this term.
Yes, sir.
So now what we can have, e of x cube minus 2x cube plus e raised to minus 1 x. So here in the example, h is given. Okay, so what we want this with the help of the step size h. Okay, now let us calculate. So what we have here, this will be x plus h bracket cube minus 2x cube plus this will be x minus h bracket cube. Is that okay?
Yes,
This
sir.
is the forward shift. This is the backward shift. Okay, so we have forward shift means we have to add the step size. Backward shift we have to subtract the step size. And here step size is going to be h. So we know the formula a plus or minus b bracket cube is equal to a cube plus or minus 3a square b. Okay, and here we'll be having plus 3ab square and plus or minus. Is that okay? You're
Yes.
getting this formula? Yes. Okay, so let us expand this. So we can have x cube plus This plus, so all the terms are going to be plus 3x square h plus 3x h square plus h cube. Is that okay?
Yes, sir.
This minus 2x cube remains as it is. For this, what we can have? Plus x cube minus 3x square h plus 3x h square and minus h cube. Is that okay?
Yes, sir.
Getting this now?
Yes, sir.
So here, what we can have is 3, this will be 2x cube minus 2x cube. It will be 0. This term is positive, this term is negative, so 0. This term is positive, this term is negative, so 0. So we will be having 3x h square and this 3x h square. So we can have here 6x h square. Okay. So now what we can have, see this term. This is what we are solving. Okay. So we get here, this is equal to delta square by E operated on f of x. So we can say delta square by E operated on x cube is equal to 6x h square. Okay. So this is how we are able to operate the operators on polynomial, and we are able to operate the combination of operators, okay, on the function as well as on the polynomial. So is there any doubt in this example?
No, sir.
All of you got this?
Yes, sir.
So that's good. Now we'll try some other example. Okay. So let us go for the another example. Are you able to see this?
Yes, sir.
Okay. So we go with the example. Prove that. Okay. So we have to prove that this happens. Okay. So let us try to prove this. So what we'll be having, we always prove with the help of the function. So let f of x be function of x. Okay. We have in this operator, we have to operate on f of x, and then we have to show that it is nothing but the same as identity or 1. Okay. So we have 1 plus delta into 1 minus delta operated on f of x is equal. Okay. So what we know the relation between delta. So delta is what? Is going to be e minus 1, right?
Yes, sir.
Okay. So what will be 1 plus delta? It will be e. Correct?
Yes, sir.
Okay. So I can replace this term and think of this term also. Okay. So let us see. We have 1 plus delta is equal to e, and this is 1 minus e minus 1 operated on f of x. So this is E and this term 1 minus delta. So what we can have 1 minus delta?
E inverse.
Yes. So it will be 1 minus E minus 1 operated on f of x. And that is equal. So let us simplify this. So we can have E, and here we have 1 minus E minus minus plus 1 operated on f of x. Okay. So is that okay?
Yes, sir.
Yeah. Should be, yes, this term should be, wait, this has to be del. Okay. This has to be del. And so this will change. So this is going to be del. Okay, what we know about del? So del is 1 minus E, right?
Yes, sir.
So what we get here?
So 1 minus E inverse.
Minus E inverse, right? So it is going to be 1 minus E inverse. So here we have, this is 1 minus E inverse. Now this is 1 minus 1 minus minus plus E inverse. So we get here E inverse operated on f of x. So E into E inverse is same as identity. So it is going to be 1 operated on f of x. So what we get here, we got that 1 plus delta into 1 minus del operated on f of x is same as 1 operated on f of x. And hence we can say that 1 plus delta into 1 minus del. Okay, this is equal to, okay, so here we proved that 1 minus 1 plus delta into 1 minus del is going to be 1. Okay. Now these are this is how we are able to prove the claims using these operators. Okay, so what we have to do is first assume the function, then operate the given operator on that function, and then find out at the final step what operator is equivalent to what next operator. Okay, so similarly, we can think of the relation between other operators. Again, so here we can have the different relation between this different operator. We'll try to solve one more example. So let's have another example. Is there any doubt in this example?
No, sir.
No, sir.
Okay, so it was easy. Okay, we go with another example. Prove that this delta into del is equal to, okay, so we have delta into del is equal to delta minus del. So this is delta minus del. And this is what we have to prove. So what we have here, let f of x be a function of x. So we have delta f of x is equal to f of x plus h minus f of x, and del of f of x is equal to f of x minus f of x minus h. Okay, is that okay? Are you getting this?
Yes, sir.
Okay. So now let us think of this operator. Okay. So what do you do? Consider delta and del operated on f of x. So what we have here, this is delta of del f of x. So it is delta of f of x minus f of x minus h. Is that okay?
Yes, sir.
Yes. Now it will be delta of f of x minus delta of x minus h. And so what we can have here, this will be f of x plus h minus f of x and minus this term. What we can have, f of x minus f of x minus h. Is that okay? Are you getting this term?
Yes, sir.
So what we have here, this I can write as, again, f of x, this is f of x plus h minus f of x. This will be minus f of x and plus f of x minus h. Is that okay? So everything we need to write in terms of f of x. Okay. So think of this. This is equal to, if I think of this term. Okay. So this is delta f of x minus, if I think of this term, f of x minus f of x minus h. So can I write this term as delta f of x minus del f of x? Can we write it like this?
Yes, sir, we can.
So here we can have delta f of x minus del operated on f of x. So what we got here? See, we are solving delta del operated on f of x. And what we got here? Delta del operated on f of x is equal to delta minus del operator on f of x. So can we say that these two operators are same? Hence, we get delta del is same as delta minus del. Is that okay? Can we write it like this? Are you getting this?
Yes, sir.
Okay. So here, what we did is we express this forward difference, we simplified it and express it as a backward difference of f of x. So it is forward difference of x minus ch, but it is the backward difference of f of x. That's what we have. The forward difference of current is actually the backward difference of previous. Okay, so here we have the forward difference of x minus h. It becomes the backward difference of next. So that is for this x minus h, the next is going to be f of x. Okay, so is there any doubt up to it?
No, sir.
Is there any doubt up to it? All of you got this?
Yes, sir.
Okay, that's good. So will you able to solve the problems based on this?
Yes, sir.
Okay, that's good.